Okay, so let me first summarize what we are kind of achieving or doing in quantum mechanics or quantum physics. And let me also compare with classical physics. Now, in classical physics, we talk about the position, momentum, the energy of the particle. In quantum physics, we don't talk about the position, momentum, or the energy of the particle, but we specify the state of the particle, let's say, in terms of the wave function. That is our crucial quantity. And compared to position, momentum, energy, etc., the other dynamical observable quantities, we have the operators. Like we have the position operator, which we show by the hat. We have the momentum operator, which we show by h bar over I del over del t. We have the energy operator, which is I h bar, no, this is x. I h bar del over del t. We have the Hamiltonian operator, which is the momentum operator squared divided by 2m plus v of x, whatever potential you have. And the Schrödinger equation basically tells us that the energy operator should be equal to the Hamiltonian operator. This is the essence of the Schrödinger equation. And, well, let's say we act them on some wave functions, x and t. Our classical observables are now just operators. Now, what is an operator? Well, in fact, you can think of the operator as just like a function. What do the functions do? You give a number to your function, and it gives you another number. That is the idea of a function. The operators, they are like functions of functions. You give a function to the operator, it gives you another function. So what does the momentum operator do? It gives you if you give a function to it, then in return it gives you the derivative of that function. Or the position operator is, well, if you give it a function to that position operator, it just multiplies that function with x. That is how we define the position operator, etc. So operators, you give it a function, it gives you back a different function in general. Not always, but in general it will give you a different function. Okay, so what about the position, momentum, and energy observables in classical physics? How do we describe them? Okay, we said that position, momentum, energy, they are now operators, but at the end of the day, it's justified to ask questions. What is the position of an object? Or what is the momentum of an object? So we should be able to give some kind of an answer to such questions. Now, the initial conditions, before continuing, we have to specify the initial conditions. Well, in classical mechanics, what do we specify? X0, P0. You know the X0, you know the P0. If you know the potential, you know the energy of the object also. So if you know these, then you know what the position and momentum of the object will be in a later time, and you also know what the position and momentum of the object was in an earlier time. In quantum physics, the initial condition is not the position and momentum, but the initial wave function. Psi of x at a time t is equal to t0. This is what you should give to the system. So this is basically how you prepare your system. In classical physics, preparation of the system consisted of determining the position and determining the momentum of the particles in the initial states. In quantum physics, the preparation of the system amounts to preparing the wave function of the system. So that should be given, or you should be able to determine the wave function from how you prepare your system. And once you know those, the Schrödinger equation tells us how it changes as a function of time. In the classical physics, it was the F is equal to m times a. This tells us how the system changes with time. And in quantum physics, this is how the system changes in time. Now, when it comes to what will we observe when we make a measurement, Well, we had already seen some cases, for example, the particle in a box case. In the case of particle in a box, we said that, okay, the energy of the system can only take discrete values, which are given by h bar squared over 2m n pi over L squared. These are the only possible energy outcomes. And the corresponding wave function was square root of 2 over L times sine n pi over Lx. Let me call the psi n. So if you measure the energy of your particle and you found that the energy was given by this expression for a given value of n, then you know that the wave function of your particle is given by this. But we had also discussed the Schrödinger equation is linear, meaning that if, let's say, psi 0 is a solution, no, psi 1 is a solution, and psi 3 is a solution, this is also a solution. This is also a solution of the Schrödinger's equation. Well, this is not exactly a solution, but let me write the time dependent. Now, you see, when we were looking at energy eigenvalues, we assumed such a time dependence, e to the power minus I over h bar E1 of t. So this is a solution of the full Schrödinger's equation. It's not seen. This is a solution of the first line over there, with E being the energy operator, not the energy value. This is a solution of the Schrödinger's equation. This is E3. Since Schrödinger's equation is a linear equation, this is also a solution. Well, what is the energy of this particle? I don't know. If you act with the energy operator on this function, this cannot be written as some number multiplied by psi of xt. This is not an eigenfunction of the energy operator. So if I measure the energy, what will be the outcome? Well, the outcome, there will be two possible outcomes for this particle. For this particle, the outcome of the energy will be either E1 or E3. It cannot be E5 for this particle. For an arbitrary particle in a box, the outcomes are all En. But this particle I'm creating in a special way, such that the wave function has this form. For this, it's just like in classical physics. If you prepare your system such that it has a particular energy, whenever you measure the energy of that particle, you will always find that value. Although all energy values are possible, since you are creating your state in a special state, in a special way, you are fixing the energy in classical physics. Here in quantum physics, I can prepare my system in a special way such that the wave function can have this form. If the wave function has this form, and then if I go and measure the energy of the particle, the energy will be either E1 or E3. Quantum physics doesn't tell me which one I will measure, but it tells me that if I measure the energy, its energy will be either E1 and E3.
Why we can combine solutions linearly, but the energy is only the energy of just one of them? I don't really get that.
You see?
Because the eigenfunction.
Right. This is the wave function of one particle. There's just a one particle. And its wave function is the superposition of two different wave functions of given energy. And if I measure the energy of that one particle, then the outcome will be either E1 or E3.
It cannot be both, but it can't just be a combination of them either.
No. It will be either one or the other one.
Why did we specifically choose the indices 1 and 3? Why did we choose 1 and 3 specifically?
This one.
Yes, for E1 and E3.
Because it's just an example.
So it can be like 1 and 3.
Sure. Depends on how you prepare your system. That is your initial condition.
So there's something behind in your
Sure. You see,
values.
here
1 and 3.
I am assuming that given psi of x at t is equal to 0 is equal to 1 over square root of 2 psi 1 of x plus psi 3 of x. If at t equal to 0, this is my wave function, at some other arbitrary time, it will look like this one. Just you can think of this, this is the classical analog of determining the position and velocity at t equal to 0. From that information, you can determine the position and velocity at a later time in classical physics. In quantum physics, if we know the wave function at t equal to 0 or at some arbitrary time, Schrödinger's equation allows me to determine the wave function at some other arbitrary time.
Hayvan sayfayı demeniz birinci bölgede, üçüncü bölgedeki olmasını ifade etmiyor.
No, it's just like I like the odd numbers. Or if you prefer the even numbers, even if you like, you can add, let's say, example 2. Your favorite number? 7. Okay, let me also add the 7. Let me add the coefficient 1 plus I over square root of 2. Why do I have those coefficients? Well, I like them. It depends on how you prepare your system. And then if this is the case, then the wave function at some other time will be just 1 over square root of 4 psi 1 of x e to power minus I over h bar e1 of t plus I psi 2 of x e to power minus I over h bar e2 of t plus psi 3 of x e to power minus I over h bar e3 of t plus 1 plus I over square root of 2 psi 7 of x times e to power minus I over h bar is 7 of times t. So if I am to find a wave function at an arbitrary time, I should know the wave function at some other time. How do you prepare your system? If I know how I prepare my system, I can determine the wave function at some later time.
Enerjinin 4 farklı değeri olduğu için 4 tane potential ball ya da 4 tane sistemin içinde bunun enerjisini değiştirecek bir şey mi söylüyoruz?
No. I'm just assuming in this example there's a single well and a single particle. And this is the wave function of that single particle.
Neden 4 tane enerji state var?
Well, it had infinitely many possible energy eigenstates. And then this is how I created that at t equal to 0. Now, how do you create such a wave function? I have absolutely no idea. But let's assume that somehow you managed to create the wave function at t equal to 0 to have this value. Well, why 4? Well, maybe if you like, you can create 7 or 10. The sum of 10 different wave functions. Now, before continuing with your questions, let me also make a distinction between possible outcomes for the measurement of some observable. Let's say O, in general it will be a function of x and p. Here O can be anything. For example, you can just put it over there, the p squared over 2m plus the potential. Or you can just put O can be p squared over 2m. It can be the kinetic energy. Or O can be just r cross p, the angular momentum. Just there O just stands for anything. So suppose there's something you would like to measure. Let's just show it by O. The possible outcomes are determined by this equation. So here lambda are the possible outcomes. For example, for the particle in a box, we had already seen that with infinite walls, the energy operator has eigenvalues given by this expression. So independent of how you create your system, whichever way you create, when you measure the energy of that system, the outcome will have this form, independent of how you create it. The analog in classical physics, if you put a particle in a box, the outcome of the energy measurement can be anything. But in the case of quantum physics, the outcome of the energy should have this form. This is, in general, independent of how you create your system. If, for example, again, if you go back to the classical analog, if you put some particle in a box, its energy can be anything. But if you put a particle whose energy is known, let's say you put a particle whose energy is 5 joules, when you measure the energy of the particle, it will be 5 joules. If you create identical such systems, when you make the measurement, all of them will give you 5 joules. Now let's go to the quantum mechanics. Quantum mechanics has this funny superposition principle. So if we have two solutions, the sum will also be a solution. So this corresponds to my wave function prepared in a special way. So that this wave function cannot have arbitrary energy. Well, in the classical analog, I'm just creating my particle with 5 joules. It cannot have arbitrary energy. The measurement on that particle will always give me 5 joules. Here I'm creating my special system with special initial conditions. And if you create your special initial conditions like this, I don't know what the outcome of energy measurement will be, but I know that it will be either E1 or E3. It cannot be E5. Why? Because I created it in a special way to start with. Or in the case of this example, if I create such a system such that this is my initial wave function, and then if I measure the energy of this particle, I don't know what the outcome will be, but I already know that there are only 4 possible outcomes for this particle. For an arbitrary particle, the energy should only have these possible values over there. For these specially created systems, in this one, I will only have 4 possible outcomes. In that one, I will only have 2 possible outcomes. They are all a single particle in the same potential well. Here there is a single particle in a potential well. Here there is a single particle in a different potential well. Or in fact, if you just think E1 and psi1 to be the energy eigenfunctions and energy eigenvalues for an arbitrary potential, the same argument will still hold.
What is the possibility of each energy state, is it 1 over n for each wave part?
Well, in this special case, you see, what is the absolute value of the coefficient of psi 1? 1 over square root of 4. What is the absolute value of the coefficient of psi 2? Absolute value? 1 over square root of 4. What is the coefficient of psi 3? Its absolute value? 1 over square root of 4. What is the absolute value? What is the absolute value of this one? 1. So it's again 1 over square root of 4. These coefficients I have chosen such that they are all equally probable because their absolute value is 0. But they don't have to be. I mean, you can create your system in such a special way that the coefficient of this one will be 10 times larger than the coefficient of this one. Then the possible measurement of E1 would be 100 times absolute value squared. The probabilities are absolute value squared. If this coefficient is 10 times larger than this coefficient over here in absolute value, the probability of E1 will be 100 times the probability of E2. Yes? That is why I have this 1 over square root of 4 over here. 1 over 4 plus 1 over 4 plus 1 over 4 plus 1 over 4 is 1. Sure, but I have to change this coefficient. It means exactly the same thing as possible different measurements of the position. You see, we were discussing about the position measurement. We said that the wave function is spread in space. So if I measure the position, it will have some probability of being here, some probability of being here, some probability of being here. It's the same thing over here. If I measure the energy of this particle, it has some probability of having an energy E1, some other probability of having an energy E2, some other probability of having an energy E3 and E4, E7.
So if our particle is not...
Sorry to interrupt. So basically, just as we said that before measuring the position of the particle doesn't really have a position. Or equivalently, you can say that the particle is everywhere. Here, before measuring the energy, the particle doesn't have a definite energy. Or you can say that it has all 4 energies at the same time.
If our particle wasn't constrained in a box, does it mean that since its position is arbitrary, it has infinitely many number of...
You see, if my particle was not constrained in a box, that would mean E1, E2, E3, I mean, the possible energy values will be continuous. If there is no potential energy, free particle, the possible energy values will be continuous, but I can still create such a wave function.
So I understand mathematically we have those discrete energy values, but is it possible to have some discrete position values maybe?
No.
Because of the wave function's property?
Well, I said no, but well, it depends. The position operator basically depends on the space. As far as we know, the space is continuous. Well, it basically amounts to saying that the possible momentum measurements, possible momentum of a particle can be infinitely large. If you can create a system in which the momentum has an upper bound, if momentum has an upper bound, the de Broglie wavelength will have a lower bound. So that will kind of create a system with discrete position values. But we don't know such a system. Except on lattice. You see, that's essentially how we treat crystals. The electron can be on one side or the other side or on the other side. No, no, it's not. There's no group over here. There's a single particle over here.
Ama bir sürü wave function toplamı bir grubun wave function olmuyor.
You see, that is as a wave. It is I mean, we can talk about the group velocity of this wave. You see, group velocity isn't really a velocity of a group. The group velocity, in a sense, you can also say, look at it as is the velocity of a group of harmonic waves. That's not a group of particles. This is a particle, a single one. A single particle which is represented as a superposition of different waves. Or the different probabilities, let's say, different energy values in this case. Now, let me just complete this over here. So classically, we have the position momentum, the observable quantities. Quantum mechanically, we have the corresponding operators. And the possible outcomes of the measurement of any classical quantity corresponds to the eigenvalues of that operator. But then you have the systems created with a given initial condition. So for such systems, if you make the actual measurements, so these two things are basically different things. You see, to be concrete, we talked about the particle in a box example, and we figured out that the energy values could only be these values. You can only create particles having one of those energies. Or you can also create superpositions of them. So there I'm not talking about any concrete system prepared in any special way. I'm just talking about the system in general. No matter how I create the system, if I make a measurement of that system, the outcomes of the energy will always have that form, have those values. Now here I'm looking at concrete systems. Again, I have a particle in a box. And if the wave function is given like this is an energy eigenfunction. This is an energy eigenfunction. This corresponds to an energy E1. This corresponds to an energy E3. If I have such a system, and if I make the measurements on that concrete system, on that special system, the outcomes will be either E1 or E3. For example, for that system, if I measure its energy, I will never measure its energy to be E7. I can create some other system. For example, if exactly the same system, but different initial conditions. By changing my initial conditions, I'm creating another system meaning another particle in the same box. For this particle can have the energy E7, but this particle cannot have the energy E5. It will only have E1, E2, E3, or E7. But no matter how I create this system, how I create the particle in this box, that particle will never have an energy, let's say, twice E1. Because twice E1 cannot be written in that form with an integer n. Now, again, if you go back to, let's say, this example, I said that if I create this wave function, If I measure its energy, I will find either E1 or E3. But then in physics, we don't do just single measurements. We do many measurements and then take their average. That average basically corresponds to the expectation value. Well, let me pick up this one. Let's say, what is the expectation value of the Hamiltonian operator? You see, H psi n is equal to E n psi n. This is what I will use. This is nothing but the time-independent Schrödinger's equation. So what's the average energy? Or the average Hamiltonian? Well, how do we calculate them? This is dx. We multiply the conjugate. Then in between we have the h xt. And in this particular example, since we are looking at particle in a box, they go from 0 to L. Well, let me write them out explicitly. We have 0 to L dx psi 1 of x E1. Now this is star psi 1 of x with 1 over 2 plus 1 over 2 psi 3 of x E3 psi 3 of x. These are, when I multiply these are the so-called diagonal terms. Then I have plus 1 over 2 from 0 to L dx psi 1 star of x E3 psi 3 of x plus 1 over 2 from 0 to L dx psi 3 star of x E1 psi 1 of x. And here we have e to power minus I over h bar E3 minus E1 of t. And in the next term, now I'm skipping some algebra. I do advise you strongly to go over the algebra yourself. So here we would have minus I over h bar E1 minus E3 of t. Again, if we already know what these functions are. These integrals will be 0. This one and that one will be 0. This is 0. This is 0. In the first line, E1 is just a constant. I can take it out. What remains is the absolute value of psi 1 squared integrated over x. That is just 1. So the average of E will be 1 over 2 E1 plus E3. You see, we said that in a single measurement, I will either find E1 or E3. But when we do experiments, we just repeat the experiment many times to make sure that it was the outcome, the measured value is not just some error in our computation or some fluctuation due to some reason. You just repeat it many times. That is, if you create your system such that this is the wave function, half of the time you will get the outcome E1, half of the time you will get the outcome E3. So the average just turns out to be, you just sum them up, divide by 2. By the way, this is not equal to any eigenvalue of the Hamiltonian. I will never obtain this energy value if I make the measurements. This is just the average of them. Yes.
Can I ask something irrelevant, kind of?
No. Okay, ask and then we will see.
Speaking of the expectation value, I don't really get the difference between absolute square of the wave function over infinite interval, which gives probability and the position expectation value. Because just that thing multiplied by x.
This is 1. This is the x. So what don't you get? What don't you get? Yes, yes. Well, look at it this way. You have already seen a similar quantity. For example, if this is the mass density, the integral of mass density gives you the total mass. It doesn't give you the center of mass. What do you do to calculate the center of mass? You multiply the position with the mass density and sum over all the position. That gives you the center of mass. In a sense, this is the same. So here you have the probability density. The total probability is 1. Then you can ask, what is the center of the probability? Like what is the center of mass? So to calculate the center of the probability, you multiply it with the position, multiply with the probability, and sum them up.
So this function gives the probability of finding a particle somewhere for whatever value we give it.
Yes.
And the expectation value gives the highest amplitude of.
No. You see, for example, your probability distribution might have such a shape. If in this case, my particle is somewhere. In this particular case, it is either somewhere over here or over there. The center of probability for this probability distribution will be over here. It's not the maximum probability. In fact, it's 0 probability. Just like in the energy example. You see, for this particle, we said that if I measure the energy, I will either find E1 or I will find E3 for that particle. If I make many measurements on particles having the identical wave function, and then average their energies, I will get E1 plus E3 over 2. What is the probability of measuring this value in this particular setup? 0. Now, the expectation value is, in fact, almost a perfect analogy to the center of mass. You see, if you look at this classroom, if you look at your masses, where do you think is the center of mass? No, definitely not there. Come on, look at the classroom. Where do you think is the center of mass of this classroom? Somewhere over there, probably. How many students are here? How many students are here? None. Just like the center of mass need not be at a position where some mass is, the center of probability or the expectation value need not be at a point where the probability is high. Of course, if there is a single region of very high probability, let's just assume, to use the analogy of this classroom, let's just assume that you all sit in these 3 seats over here. In that case, the probability of finding a student will be huge over here, but negligible over there. Then the average will be close to the position of large probability, but it doesn't have to be. Well, I already stated it, I don't know, a couple of times. If you make many measurements of energy of the system, take the average of those measurements, this will be what you will see. You see, quantum mechanics does not tell us the outcome of a single measurement, unless you create your system in a special way. But it does tell us what the outcome, the average outcome will be if you make many measurements. And most of the time, that is what we do in real life. You see, when I'm looking at you, I'm actually making many measurements of many photons reflecting from you and coming to me. Sure. You see, that was a case where we have such a wave function. If the wave function is like this, if we have such a wave function, then the center of probability is over here. It just tells me that your wave function doesn't look like this one, but mainly looks like this one. So if I make many different measurements, they will be all localized around this value with some very small spread. Now let me just write one more equation about the expectation values. You see, if you look at over here, when I was looking at the expectation value of the energy, you see, in fact, there are these time-dependent terms, which in this case, they cancel, they are zero. It basically amounts to the saying that the energy is conserved. Energy cannot have any time dependence. But here, instead of calculating the time dependence of the energy, I could have calculated the time dependence of, let's say, position of this object. It will be changing with time, the expectation value of the position. So we can talk, I mean, we will come to this point later on. But let's say, if you calculate how the expectation value of the position changes as a function of time, what you will find is expectation value of P over M. Or the expectation value of P will be just M times the time dependence of the expectation value of position. Well, if you look at how does the expectation value of position changes as a function of time, if you try to calculate this one, what you will find is that this is actually equal to minus the expectation value of gradient of the position, or expectation value of the force. So in a sense, classical mechanics is still containing quantum mechanics in the expectation values. What does classical mechanics tell us? It tells us that the momentum is mass times the velocity, time dependence of position, and the rate of change of the momentum is equal to the force. You will still get these. So it's not such a great surprise that classical mechanics works, at least for large objects. Okay, I will just take 10 minutes from your break, and let's just go over this problem of particle in a potential valve. Because in the next hour we will have this questions and answer where you were allowed to discuss. Okay, so as a reminder, we had such a potential. We divided our system into region 1, region 2, and region 3, and we were looking for, this is E is equal to 0 line, or U is equal to 0. We were looking for a solution of H psi is equal to E psi, where E was less than 0. So essentially we are trying to see if we can put a particle in this such that it will have a negative energy. Well, does this exist in classical physics? Yes, because you see, any particle over here has a negative potential energy. If the kinetic energy is smaller than that potential energy, the total energy will be negative, classically speaking. So classical physics allows negative energy is not a problem. That is basically reflects the fact that we define this point as our zero potential. And now we said that, okay, so let's look at our in region 1. In region 1, our equation read like this, minus h bar squared over 2m, second derivative of psi with respect to x. The potential is 0. This should be E psi, which we defined as minus h bar squared over 2m times kappa squared psi. And then we said that this solution, this equation has a general solution of a times e to power kappa x plus b times e to power minus kappa x. But you see, the integral of psi squared from minus infinity to infinity should be 0, should be 1. Well, if we have this term, this diverges as we go to x to minus infinity, so its integral will not be finite. So I cannot have this term. So in region 1 is a times e to power kappa x. This is where we had left on Thursday. Now, if you study the system in region 3, again, the potential is 0. So here there is no potential term. We have exactly the same equation. We can make exactly the same derivation. And the general solution will have this form in region 3 also. But in this case, x, again, the wave function should be, the square integral should be finite. But as x goes to infinity, this diverges, it goes to infinity. The wave function is not finite as x goes to infinity if I have this term. So this term should be absent in region 3. So my wave function in region 3 should have this form. Well, two things to note. They are not oscillating. You see, we looked at particle in a box. It was oscillating. And here, this is similar to particle in a box, but it is not oscillating. But you see, energy less than 0 basically amounts to saying that the energy is somewhere over here. So classically speaking, the particle can only be in this region. Because in this region, if the total energy is like this much, if my particle is over here, the kinetic energy would be negative. Classical physics doesn't allow it. So it cannot be in region 3. It cannot be in region 1, classically speaking. So those are called classically forbidden regions. So let's say that my particle, let's say that this height is 5 joules. So a particle at rest over here will have a total energy of minus 5 joules. So let's say it has a kinetic energy of 1 joule. That means my particle has a total energy of minus 4 joules. Well, minus 4 joules will be the kinetic energy plus the potential energy everywhere. If my particle is over here, my potential is 0. So minus 4 joules would be the kinetic energy. But that's not possible. So my particle cannot be here. Its energy is not enough to leave this range. So that is why region 1 and region 3 for such a particle will be forbidden in classical physics. You will never find your particle over there. Your particle will not feel what is in region 1 and what is in region 3. But now we have these wave functions. They are non-zero. My particle has a non-zero probability to be in region 1 or region 3. So let's compare it with the infinite well case. Yes, if my potential were infinite, we had found that one of the ground state looked something like this. This was the ground state wave function for infinite walls. Now the potential is not infinite, so we know that outside my wave function need not be 0. It will basically look like something like this. It will go to 0 exponentially. Well, it will look something like it will spread into the classically forbidden region, in a sense. So there's still some finite probability of observing the particle here, some finite probability of observing my particle over here. In between, we will see that it looks more or less like our infinite wall case. Or if you look at the first excited state, classically, no, in the infinite potential wall case, it looked like this. Now it will spread out a bit. So it will start something like this, go up, go down, come here, and it will spread out a bit. In between, in the classically allowed region, it will oscillate. That's the general feature of the wave functions. In the classically allowed regions, they oscillate. They are actually oscillating waves. In the classically forbidden regions, they will have exponentials. Now let's write the wave function in region 2. Well, the Schrödinger equation will be this much then, plus minus u0, psi is equal to E of psi. And remember, E is less than u0. So minus, no, sorry. No, let me forget it. Minus h bar squared over 2m, d squared psi by dx squared. This should be equal to E plus u0 psi. Now, E plus u0 this is larger than 0. You see, before I didn't have this u0 term, I only had the E term, it was less than 0. Now I add this u0 term, now the total energy is large, E plus u0 is larger than 0. You see, the energy I'm looking for is somewhere over here. This is minus u0. This is E. So this height is E minus u0, which is larger than 0. This height. Well, since this is positive, I will define it as h bar squared over 2m k squared. So that now the solution is this much, this one. And this is the equation. The solution is just, let me call it C1 sine kx plus C2 cosine kx. They will be oscillating, because here now it will be negative. Anyway, I will not continue with the solution. For me, what would be important at this point, at least, will be this one. The wave function is non-zero even in the classically forbidden region. If you like, you can just continue along this line. Wave function should be continuous at x is equal to 0, which basically means that psi 1 at x is equal to 0 should be equal to psi2 at x is equal to 0. And also at psi is continuous at x is equal to L, which will tell me that psi2 at x is equal to 0, x is equal to L, should be equal to psi3 at x is equal to L. And then you have derivative of psi is continuous, which will tell you that derivative psi1 prime at x is equal to 0 is equal to psi2 prime at x is equal to 0, and psi2 prime at x is equal to L should be equal to psi2 prime, no, psi3 prime at x is equal to L. So we don't know A, we don't know B. You see here we have in psi1 we have one unknown A, another unknown B. And then here you have two more unknowns, C1 and C4. You have four unknowns. And here you get four equations. You have four unknowns and four equations, plus one more equation. Well, if you have four unknowns and if you have five equations to be satisfied, in general, you don't get any solution. There won't be any solution. So we have to lower the number of equations, which basically tells us that 1, 2, 3, and 4, we should have only 3 independent equations, not 4. Well, okay, I will not go into, we will do that when we are discussing the tunneling effect, but what will happen is equation 1 plus equation 2 plus equation 3 plus equation 4 will have this form, A, B, C1 and C2 equal to 0. Here on the left-hand side you will get some matrix that depends on E. When does this equation has non-trivial solutions? Let's say this matrix is some matrix, let's call it M. Determinant of M, which will be a function of E, should be 0, which will tell you the allowed values of E. So the possible energy values will again be quantized. Well, the explicit expression will not be as easy as in the case of the infinite potential well, but the basic idea is over here. Anyway, let's give a 5-minute break, 5 minutes, and then we will continue. We don't have any psi-4. I have 4 equations. I don't have psi-4. You see, equation 4 is a relation between psi2 prime and psi3 prime. The wave function has to be continuous, and its derivative should be continuous. Well, in fact, what we have used as boundary conditions, our wave function should go to 0 at infinities. That is one thing we used. Second condition that we are using, the wave function should be continuous. The third condition that we are using is that its derivative should be continuous. The wave function has to go to 0 at infinities because we know that our particle is in the box, or quantum mechanics just allows it to extend a bit further, but it's somewhere over here, definitely. It cannot be at infinity. At infinity, the probability should be 0. Okay, your 5 minutes started. Okay.